Welcome to Lecture 8. This will conclude our series of lectures related to the kinetic theory of gas. We've learned a great deal. We were able to connect pressure and density of kinetic energy. We were able to get a derivation of the ideal gas law. And we are going to try to see how we can understand things a little bit better here by talking about collisions and mean free path. In fact, in our kinetic theory of gas, we suppose that the gas do not interact with each other others than through collisions. This is a very complicated thing. Collisions are purely quantum mechanical effect. They involve a number of advanced effects that we will not study in this course. But we can actually learn a great deal about them by moving forward with this idea of ideal gas framework. And in fact, this is the only ingredient that came into the ideal gas description. So that's what we are going to do. And we will actually be able to connect a number of properties with observed properties that can be observed. So what we are going to spend time talking about is the mean free path. I will provide a definition of what the mean free path is in a second, and also the collision cross section. So let's try to see what's happening. So before we get into the details, let's try to set the stage. If you remember, in a previous lecture, we discussed the average velocity of gas at room temperature. For example, we actually look at in nitrogen, and we discussed that we found an average velocity of about 500 meters per second, very similar to the speed of sound. And the point we made at that time was that that is a very high speed. So molecules are really moving about very quickly. And so what all that's happening here is that there are collisions, collisions between them, between the atoms, and also collision with the container, the walls of the container. So basically, if you were to put two different gases together, they will mix very quickly. But of course, it's not quite the case. I mean, it goes very quickly, but not as quickly as 500 meters per second, of course. Because there are collisions. So it's very important to understand the collisions that happen between molecules. So as I mentioned a minute ago, collisions are the details of the collisions is an advanced topic. I mean, it can involve a number of effects like Pauli exclusion principle and other principle can involve a change in electronic structures and things like that. We are not going to go there. We are going to stay in a kind of a in the classical description. In fact, we will simply try to bunch all those quantum mechanical effects within some heuristics like cross sections and time between collisions. And then we will just say that it happens. The collision happens. The collision do happen, and they yield. We can describe them as essentially randomizing the velocity of the gas molecule. Okay, so this is what we're going to do, and you'll see that we can understand things pretty nicely from this. All right. So the first topic I like to talk about is the mean collision time. Mean collision time essentially means how long will a molecule in a gas travel before it will collide with another molecule on average. Okay, so that's going to give us the number of collisions, the amount of collisions in a given time as well. So for that, let's try to see what heuristics we can calculate. So we are going to suppose the molecule travels at speed v, and it's going to, this is the really large approximation we'll make, is that particular molecule will travel at speed v, and it will travel among others which are stationary in its own frame. Okay, so this is an approximation, as you can imagine, but it's going to help us help us understand what's happening, and then we will relax that approximation at the end of this screencast. So imagine that the molecule is moving. Suppose everything is frozen. Think a little bit about the movie Matrix. Everything is frozen, and you move among the frozen object. Okay, this is the idea here. So what we are going to suppose is that the molecule will be described by a cross-section, sigma. We will spend quite a bit of time talking about sigma in a few minutes, but imagine that the sigma is like a toddler who needs his personal space, and this is essentially the molecule's personal space. This is the space, this is the surface area that the molecule, if you stay out of that surface area, you do not interact and you don't bother the molecule. This is essentially the idea. So this is a cross section, right? I put it in green on the right hand side of this slide. Now, of course, that molecule moves a certain velocity, v. Of course, the velocity is constant because this is between collisions, so there is no transfer of momentum or anything like this. So if during a time dt, the distance that's going to be traveled by the molecule would be v dt. So in other words, the volume that's going to be swept during that time dt would be sigma times v dt. All right. And so remember that we suppose that that the molecule is traveling across among other molecules that are frozen in space. Okay, but they exist, but they are frozen in space. It turns out that if another molecule is in that volume, there will be a collision for sure. Because remember, the sigma is the personal space of the molecule. So if there is another molecule within that volume, there will be a collision for sure. Okay, that's the idea. So I hope this is very important to understand all those concepts before you can do the math. Okay, so here the risk is that you do the math and you say, okay, the math are easy, they're actually fairly simple. And then you say, okay, I understood. But what's really important here is to understand the concept and the definition. Okay, all right. So if I have a density of molecule, which is n, which is the number of molecule per unit volume, then the total probability of a collision is going to be n sigma v dt. Okay, n sigma v dt is sigma v dt. Sorry, is the volume that I have, the cylindrical volume that I showed on the right, and n is the number of molecule per volume. Okay. Now, just before we lose our mind a little bit, we are talking about probability. So let's check the units. Sigma VDT is, of course, a volume, so it's measured in cubic meters, right? Sigma is square meters, and VDT is it's a distance. And N is the number of molecule per unit volume. So basically, this number N sigma VDT is indeed just a unitless number, which is good for probability. Okay. Very nice. Now let's try to go a little bit a step further. Now that we have understood where the n sigma v dt means. Now we are going to calculate the probability that we do not have a collision up to time t. Okay, so let's try to see the probability to not have a collision up to time t plus dt. Of course, we know if we use Taylor's expansion that probability pt plus dt will be pt plus dp over dt dt. That's the first order. Basically, that's the first order. This is either a Taylor expansion or it's the definition of the derivative really of dp over dt. Okay. At the same time, the probability to not have a collision up to time t plus dt is the probability of not having a collision up to time t times the probability of not having a collision between time t and time t plus dt, right? So this is an example of where the math is easier to say than the English. So basically, the probability to have no collision at t plus dt is the probability to not have collision up to time t times the probability to not have a collision during the interval dt, right? And this is nice because the second part there, 1 minus n sigma v dt, is known from what I showed in the previous slide. So in the previous slide, I said, what's the probability to have a collision during time dt? And this was n sigma v dt. So here, the number 1 minus n sigma v dt is the probability to not have a collision during time dt. All right? So that's all good because now I have two different expressions for p of t plus dt, so I can equate them. And when I equate them, I get an expression for the derivative of the probability. And I have a nice expression where the derivative of a function is proportional to that function. And we know what we can only have this when we have an exponential, right? So exponential, it's the only function when we take the derivative, the first derivative, you get the same function times a constant. And the constant is usually the one that's in the, it's what you find in the argument of the exponential. So you find that the probability of to not have a collision up to time t is the exponential, e minus n sigma vt. Very nice. Okay, very nice. Now, suppose that we want now to calculate the probability that is no collision up to time t, that we know what it is, and then a collision in the next time dt. Well, we have all the ingredients to calculate this, and the ingredients, of course, are the first term there, the exponential, which we just calculated, probability of no collision up to time t. And the second term, n sigma v dt, remember the cylinder I drew a couple of slides ago. This is the probability of having a collision during an interval time dt, okay? So if you integrate this over all the time, you will find that it integrates to 1 as a good probability should do, okay? Nice. Now we have the probability of no collision up to time t and then the collision at time dt. And of course, that's nice because if I integrate, if I can actually obtain the mean scattering time. Remember, this is the time on average that happens between two collisions, okay? So I can do that, and of course, I get this by the integration of the expectation value of time t, right? So the expectation value is the integration of time times the probability of having a collision at time, no collision up to time t and a collision time dt, okay? So this is the usual expectation value of the time since we have the probability distribution that's written in larger letters on the top of this slide. So we can calculate that average time elapsed between collisions. And I can do a change of variable here. Or we can just integrate. It's not a very complicated integral, but the integral can be written like this by making a change of variable. And of course, we end up with an equation that's a fairly well-known integral, and that integral can be calculated using formulas, of course. This is not very complicated. The point is that thanks to this, we can do the integration, and we find that the time between collisions on average is 1 over n sigma v. So we already find a very important result, is that the time between collision is on average this value. Of course, we can already think a little bit why this is so. If we have a very large cross section, basically that means that the cylinder I showed you before would use a large volume, if you will. The time between collision will be small, right? Because the probability of finding another molecule within that volume is going to be large. Of course, that volume of the cylinder also depends directly on the velocity. So if I sweep more volume, the cylinder is longer, basically, then the time between collision is also going to be shorter. And of course, the larger the density of molecule, the smaller the time between collisions. So it all makes sense that the time tau will be 1 over n sigma v. Okay, let's try to spend a bit more time on the collision, on this idea of collision cross section. And for this, we are going to introduce the concept of the Hart sphere potential, which is a very simple interaction potential. It's not an interaction potential per se. I mean, it's an interaction potential which is basically the simplest possible between two particles. Let's try to think a little bit how it works. So for this, we are going to give an impact parameter for each molecule. And let's say here we have two different molecules, which has one has a kind of a radius A1, and the other one is a radius A2. Okay. So we are going to discuss this radius or impact parameter as a distance of closest approach that would result if the molecular trajectories were undeflected by the collision. In other words, this is the closest distance, A1 for example, it's the closest distance that a particle should reach. I mean, this is the largest distance that another particle should be away from the center to start having a collision. So anything above A1, if any other particle gets further than A1 from particle 1, then there will be no collision. Basically, that's what it means. Now, that also means that if the other particle has an impact parameter A2, we have the same thing for that particle. And so we are going to define what's called the Hart field potential. The Hart field potential is essentially the simplest potential. It says that if the distance is larger than A1 plus A2, there's no interaction whatsoever. But if the distance is smaller, then there is a perfect interaction and collision. It's basically, when I say perfect, means that the force in that case is also infinite. That means that the two particles will bounce off each other. Okay, so there will be a perfect collision, if you will, perfect in the sense that there will be transfer of momentum for that distance. Okay, so in other words, for the Hart sphere potential, there is only collision if the distance between the two is smaller than A1 plus A2. Okay. Okay, so the impact parameter here, of course, is not A1, A2. Is actually the impact parameter is the distance between the two particles. So it's going to be A1 plus A2 in this particular case. Okay. All right. So let's try to go a little bit further than this. So basically, the idea is that if the distance between the two particles is smaller than A1 plus A2, then there is a collision. Otherwise, there is none. That's the idea. Now let's go back to what we discussed before, and think about again to the cylinder, and let's try to connect the cylinder with those A1, A2 that we just discussed. So suppose that you have a particle A1, particle 1 that's moving with velocity v, and it has a effective radius A1. Okay. And remember that all the other particles, all the other molecules are all shown as larger, but that they could be smaller. That it doesn't matter. They all have their own radius A2, which is drawn as being larger than A1, but could be something else. Could be the same too. And they're all frozen in space. So the idea is that which one are going to interact with which particle are going to interact with particle 1. Well, in this case, you see that the collision will only take place if the center of the other molecule are inside the tube of radius A1 plus A2. So basically, the particle A looks like some of the sphere is inside the cylinder, but the point is that it will not interact with particle 1, okay? Because it's outside the cylinder. Now, particle B will definitely interact because you see that the two spheres are going to overlap. And particle C will interact just so. So basically, this is the idea that for particle C, the distance between the two particles would be A1 plus A2. So we consider that this is part of the potential that's infinite, but it's just so because the particle C is on the cylinder, okay? So this is what we call the cross-section sigma that we discussed about. So this is the personal space. So if the other particle do not get into the cylinder, so the center does not get into the cylinder, then they will not interact. It's called what's called the cross-section, okay? So a personal space. So the area of the tube is called the cross-section sigma, and then as we discussed, and of course that cross-section will be that circle that's of surface P A1 plus A2 square. Okay, So that's what we call the cross section. And we of course need to know what those value A1, A2 will be, but this is a good idea of where we get. These are heuristics again that you would require a more detailed understanding of the chemistry and the quantum physics happening in order to get a value for sigma, but we can obtain it experimentally. So we can ask ourselves, is the Hart sphere potential correct? It's basically the simplest potential that we can use. It turns out that it works well because sigma, so sigma, which is pi A1 plus A2 square over 2, is essentially temperature independent. So if you see that that the difficulty is actually a little bit simpler. It's actually mostly temperature independent so long as temperature is low enough. Because when the temperature gets higher, that means that the velocity of the particle gets higher as well, and the interaction between two particles will only happen if you have a head-on collision. In other words, the cross section appear to be a bit smaller at high velocity, which corresponds to high temperature. So basically, sigma is pretty much constant at low temperature, gets smaller at higher temperature, but it's a pretty good approximation. Now we have time to we can move to the other topic, which is the mean free path. So now we found we discussed already the time between collision tau, and we found it is 1 over n sigma v. Now we can think a little bit about the mean free path. The mean free path is very much related to the time tau. It's the distance on average that a gas molecule will travel before it collides with another particle. Okay, this is called the mean free path. We call it free path because during that interval between collision, there's no force, no other interaction. So it's a free particle basically. So it's the path during which it's free. So you would think that now that we have the time, we could say, well, it's very simple. The mean free path should be the average velocity times the time, right? However, if you do this, you will see that things do not work out. There is a systematic error, and the reason why there is an error is because of an approximation we made at the beginning. It was not really an approximation; it was a simplification, more like it. It's the idea that we consider the molecule and all the molecule being frozen in space. So you remember we did that when I discussed how the movie Matrix, where everything is frozen and you move among the other particles. So basically, that's the idea. The idea is that we should really consider the relative motion of a gas molecule relative to the other one, just instead of just consider the other one frozen. So what we would need to use here for the velocity, for the average velocity, is not exactly the average velocity, but instead we should consider the expectation value of the relative velocity. So I'm sorry here I didn't put any animation on this slide, but the idea of relative velocity between two particles is that what we can calculate is the square of the relative velocity, which would be v1 square plus v2 square minus 2v1 dot v2, where the dot is the dot product. I do this because the expectation value of the square of the relative velocity will simply be v1 square, the expectation value of v1 square and v2 square, since the expectation value of v1 dot v2 is 0, since all the angle between the two velocities are 0. If you want to do it mathematically, it's because you're going to have a cosine theta that's going to show up, but since you have to consider all the theta, the average is 0, right? Over a period, cos theta is averages to 0. So now, what we would really need is expectation value of VR, relative velocity. But what we have is expectation value of VR square. If you go into detail of the Maxwell-Boltzmann distribution, you will see that taking the square root of the expectation value of VR square is pretty much the same is very close to the expectation value of VR. So that's what we will use. There is a small mistake, but we can use that. So in other words, the expectation value of the relative velocity is pretty much equal to square root 2 of the expectation value of velocity. So you see there is a square root 2 term there that increases basically the space, the length. No, that decreases there's going to decrease, sorry, the the mean free path, right? Because of the relative velocity, the fact that the other molecules are also moving. So if we plug that in the equation we had before, we find that what we end up with is that the mean free path lambda is actually 1 over square root 2 n sigma. And this is much closer to what we would expect from an experimental measurement. Now, we can also, and this is on the right-hand side of the blue arrow there, we can also substitute the density of particle n using the ideal gas law, right? The ideal gas law being PV equal KBT. Now, lowercase n is uppercase n divided by volume. So we can just plug that in and end up with an equation for the mean free path as a function of temperature, pressure, and also sigma. Okay. So what we find from this equation there is that if you increase the pressure inside a volume, or a given volume of gas, the mean free path is going to go down, which is not really surprising. Increasing the pressure means you're increasing the probability that two particles will collide. And of course, same thing for sigma. If you increase the cross section, that means that there is a larger chance that two gas molecules will collide, and therefore the length, the distance that the particle needs to travel will be lower. So another way to look at this is to keep in mind this idea of the cylinder I showed you, with that has a base sigma and a length and height v delta t. If sigma increases, the length of the cylinder, if you will, can get smaller for a given volume. That's the reason why we have this here. Now, be careful about what you say about temperature here. Temperature is on the temperature is on the numerator, but pressure also depends on temperature. So we have to be careful about how to make a conclusion about change in temperature will have changes in the mean free path, because we have to be careful how pressure changes too. Okay, so to summarize this here, we conclude this kinetic theory of gas, description of kinetic theory of gas, which were applications of the Maxwell-Boltzmann equation, and which allowed us to calculate the pressure and find that we have a match with the ideal gas law. But we can also apply this understanding to calculate the collisions, because collisions is the main mechanism of gas to know that there are other gas molecules around. So we found the mean scattering time, which is the average time between two collisions, and then we also calculated the mean free path. So we calculate all this, and then we realize that all the calculations and description we've done were based off the fact that a particle is moving among other particles that are frozen. And then we found that by doing this, allowed us to do calculations, yes, but there was a systematic error due to the fact that other particles are moving as well. So the actual expectation value of velocity we need to use is the relative relative velocity, expectation relative velocity. And so the reason why what we use is the expectation value of VR instead of the expectation value of V. This concludes this screencast. We are going to move ahead with the next screencast, which will be on the next topic of our adventures in thermodynamics. And thank you very much. See you later.